Good day, viewers all over the world. Today we want to talk about homogeneous equation. We are still under solution of first order differential equation. The first one that we considered in the last lecture is that separable first order differential equation. So that is, if you are given a differential equation, if you are able to separate it in such a way that we have x and the x at one side of the equation, then y and the y at the other side of the equation, just introduce integral sign, then you get the solution. But under this now, if we cannot solve a differential equation by method of separating the variables, then we solve by substituting u with y is equal to vx. That is, let's consider this example 1 under homogeneous equation. How do we know that this equation is homogeneous equation? If you check my videos on first order differential equation, for this to be homogeneous, this is what we are going to check if f of tx, ty is equal to f of x, y. If we are able to check this, then it shows that that equation is homogeneous. It shows that that equation is homogeneous. That is, it shows that that equation is homogeneous. So if I have to show this, so what do we do here? If we have f of tx, ty, that will be, in this case now, f is a function of dy dx. So that's what we have there. So dy dx is this. Then wherever you see x, you put tx here, plus 3ty all over 2tx. T can come out at the numerator. What do you have there? X plus 3y. At the denominator, we can have t2x. It's just a matter of rearrangement. If t cancels t, what do we have left? Is it not the same thing as what we have here, which is the same thing as f of x, y? So we have been able to show that this is f of ftx, ty is same thing as f of x, y. So it shows that this equation that we are given is homogeneous. So since we know that the equation is homogeneous, then since the equation is homogeneous, of course, before we test for the homogeneity of this equation, we are sure that this equation cannot be separated. We can't use variable separable in this equation, because there's no way you can write this equation in such a way that x and the x will be at one side, then y and y will be at the other side. That's why we have to test for the condition for homogeneous, for equation to be homogeneous. Since we have tested that and we are sure that this equation is homogeneous, then we go ahead and applied y is equal to vx. That is, under homogeneous equation, we cannot solve it directly. We have to use this. That is, we now see this is what we say. So we have been able to show that. So the y, the x will be what? X plus 3y all over 2x. We are sure that that equation is homogeneous. We now let y to be equal to vx, so that dy dx, we can't do this directly. Dy dx will be equal to, if I pick this, I will differentiate this. This is v, plus if I not pick this, I will differentiate this, dv dx. Please, under homogeneous equation, we have to be very careful. We cannot solve this equation directly. So wherever we see y here, we change y, we change it to vx. Then wherever we see dy dx, we change it to this. That is, instead of dy dx, now we are going to have v plus x dv dx to be equal to yeah, wherever we see x, we leave it as x, to be equal to x plus, instead of 3y, we are going to have 3vx all over 2x. What can we say about this equation? X is common. We can bring out x into bracket 1 plus 3v all over 2x. Okay, that is what we are going to have there. So x can take care of x. X can take care of x. So that at the end of the day, we have v plus x dv dx to be equal to 1 plus 3v all over 2. So if you check this last equation now, everything that we have there is x, v, dv, and dx. So we should be able to rewrite this. We now rewrite this. We can, at this point now, we can go ahead and use we can go ahead and separate this equation. since we know it, we can separate this equation in form of x and the dv. We can in form of v and dv, then x and the x. Let's see what will happen if we try to separate that equation. That's what I'm about to write now. So we can go ahead and solve and separate that equation. Then from there, I can take v to the other side, so that I have x dv dx. I have x dv dx. Let me change the marker. I have x dv dx to be equal to 1 plus 3v over 2 minus v. I start to take v to the other side. So here now, let's see the SCM. Here will be 1 plus 3v minus 2v. So that we have x dv dx to be equal to 1 plus v all over 2. That's what we're going to get. So at this stage now, we can actually separate everything. At this stage, they are separable. So what we are trying to say is that if I use 2 to multiply this place, if 2 should come to this side, I will have 2x dv. If I cross multiply, let's say I cross multiply 2 into bracket 1 plus v dx. This is what I'm going to get. So if I cross multiply, that's what I'm going to get. If I cross multiply, that is what I'm going to get. Then if I divide both sides by 1 plus v, so this will cancel this. I can also divide through by x. I will divide through by x. At the end of the day, x will take care of x. What I'm going to get finally will be 2 all over 1 plus v dv. Okay, that's what I'm going to get here. Then at this side, I'm going to get 1 over x dx. So at this point now, we have been able to separate everything. V to dv, then x to dx. So if we are able to separate this now, we just introduce integral sign. Then we just integrate and get our final answer. We integrate and get our final answer. So what do we do here? If we integrate this side, 2 can come out. We have 2. The integral of 1 plus v dv will be n 1 plus v. That's what you are going to get there. Then integral 1 over x dx will be in x plus arbitrary constant. Of course, that constant can be maybe in a or something. So we can say, let's see, equal to in a. It's just an arbitrary constant. So that these 2 can come up. We can have n into bracket 1 plus v squared to be equal to maybe in x plus in a. We try to represent this as in x plus in a. So this can be equal to in ax, is logarithm. N is logarithm in 1 plus v all squared. If I take exponential of both sides, I'm going to have 1 plus v all squared to be equal to ax. That's what I'm going to get. That's what I'm going to have. But we are going to recall. We recall that y is equal to vs. The question is in form of dy dx, not in form of v. But since we cannot do it directly, we have to let y to be equal to vx. So we now recall back now. So what is, if y is equal to vs, then invariably v will be equal to y all over s. So whenever I say v here, I'll change it to y all over s, so that I'm going to have 1 plus y all over x all squared to be equal to ax. And then if you take the SCM will be x here. So we have x plus y. We have x plus y all squared to be equal to ax. So we are just trying to rewrite everything so that at the end of the day, we now have x plus y squared to be equal to ax squared. That's what we have. We might try to stop the answer at this point, or if we want to continue, we might try to stop at this point, and if we can still continue. Or if you start to stop at this point, you get your full mark. Or we can just say take the square root of both sides, so that at the end of the day we have x plus y to be equal to, that will be x plus y to be equal to x. That will be equal to, when we take the square of both sides, x square root of a. That's what you're going to get. Then y can be equal to x minus x square root of a or something. So we can start to stop at that point. So the basic idea on this homogeneous equation is that Any equation that we cannot solve directly, that are not separable from the onset, then we are expected to test for homogeneity. How do we test for homogeneity? We just say, when we go through the video of solution of first order differential equations, we say if f of t, ts, ty, if you can write it as f of x, comma y, that is, if you can bring out t, if t can be taken out from this equation, and we're able to write it in this one, it shows that that differential equation is an homogeneous equation. And if we are sure that that equation is an homogeneous equation, we cannot solve homogeneous equation directly. We normally make use of the let statement. Say y is equal to vx. So that by the time we differentiate, we are going to have the y dx, which will be equal to v plus x dv dx. So in that given question, wherever you see dy dx, if we represent it with what we have here, then we solve that equation using the separable, variable separable. And once we get to a particular point, as we arrive at this point, we recall back that y is equal to, because the question is given as the y dx, not the v dx. We substitute back the value for the value of v, then we'll be able to write our final answer as what you have on the board. So this is how to solve homogeneous equation. This is how to solve homogeneous equation. Thank you.